Shifting to a more practical discussion, when it comes to 3D modeling, one of the most efficient methods for creating accurate models, particularly when working with 2D data, is parametric modeling. Parametric modeling is an approach that uses known geometric ratios, directrices, and parameters to generate complex models from simpler, scalable elements. By starting with a basic geometric shape, such as a cylinder, sphere, or rectangle, you can quickly build a solid foundation for your model. This allows for ease in refining and adapting the design as needed, whether manually or using software tools. Manual modeling can also benefit from this approach by using basic geometries and mathematical properties to construct 3D forms step by step. Just as you might sculpt with clay, you guide the process with mathematical precision to ensure accuracy. In essence, parametric modeling acts as a bridge between raw mathematical theory and creative design, offering flexibility for both manual and computational modeling tasks. Starting with simple, known shapes provides a structured framework for constructing more complex and detailed forms. This approach allows designers to refine their models by adding features like arcs, lines, and triangles, all of which are grounded in mathematical principles. The significance of triangles cannot be overstated. In CAD, computer-aided design, and 3D modeling, triangles are the most basic and stable polygon, forming the foundation for defining any surface. They are inherently predictable because they are defined by only 3 points, making them a reliable tool for modeling. This principle is crucial when working with curves, irregular surfaces, or complex shapes. Triangles form the backbone of computational geometry, as even highly complex surfaces are ultimately broken down into a mesh of interconnected triangles. This technique allows for computational efficiency when rendering and simulating models. For example, in early video games, the graphical meshes used were bulky and angular because they relied on triangular meshes. This simplicity made it easier for computers to process the graphics, consuming less power and memory. Today, with advances in computing power and the integration of more sophisticated trigonometric functions, video games feature highly realistic graphics. However, the fundamental use of triangular meshes still underpins this technology. In 3D modeling, when you manipulate features like arcs, lines, or additional triangles, you're adjusting the triangular framework of the model. Whether you're smoothing edges, sharpening features, or adding new details, these edits ensure the geometric integrity of the model is maintained. Understanding the relationships between triangles and the trigonometric functions that govern their shape and placement provides a deeper understanding of how CAD tools work and how geometry drives the design process. Ultimately, the principles of geometry and trigonometry are essential to achieving precision, adaptability, and creativity in CAD drafting. Whether you're working with simple parametric shapes or intricate, freeform designs, these foundational principles enable you to model with confidence and efficiency. The concept of precision in mathematical calculation is vital when working with triangles in CAD modeling, particularly when triangulating shapes for larger designs. The principle of measure twice, calculate once underscores the importance of establishing accurate initial measurements. These measurements are used to define 2 points that create one side of the triangle. The accuracy of these 2 points determines the reliability of subsequent calculations, helping to avoid errors in later stages of the modeling process. Once these 2 points are established along the x-axis or any other axis in the coordinate system, they define a straight line segment, which forms the base of the triangle. To complete the triangle, a third point must be located, which is determined based on its relationship to the base. This third point could involve factors such as height, which is the perpendicular distance from the base to the point. In some cases, the third point's location is also defined by an angle, which is calculated using trigonometric functions like sine, cosine, or tangent. These functions help determine the relative position of the third point along the y-axis, z-axis, or another coordinate axis, depending on the triangle's orientation. With the base defined and either an angle or height determined, the coordinates of the third point can be calculated using standard trigonometric equations. For example, if the length of the hypotenuse and the angle are known, the position of the third point can be derived through a specific formula. This method transforms the basic measurements into precise coordinates, allowing for the construction of a triangle that can later be used as a building block for more complex shapes and structures. Triangular modeling plays a significant role in simplifying the design process. Once a triangle is defined, it can be manipulated, rotated, scaled, or transformed to fit into larger designs. By breaking down complex shapes into simpler triangles, the entire modeling process becomes more manageable, and the calculations involved become easier to handle. This method is particularly effective in CAD, where a series of interconnected triangles can be used to form more intricate shapes without overlap, ensuring precision in the final design. In the context of CAD software, ensuring the base of the triangle lies along the x-axis simplifies calculations. This alignment reduces complexity, particularly when dealing with complex shapes or working in a three-dimensional space. By fixing the base along the x-axis, the third point's position becomes easier to compute, using known values such as the length of the hypotenuse and the given angle. The position of this third point, denoted as x3, can be calculated using the formula x3 equals x1 plus length of hypotenuse times cos theta. In this formula, x1 represents the first point, and theta is the angle formed by the base and the hypotenuse. By calculating the horizontal and vertical components using the cosine and sine functions, the third point's coordinates are determined, completing the triangle. For example, suppose the base points are 0, 0, and 4, 0, and the hypotenuse is 5 units with an angle of 30 degrees. Using the formula, the third point, x3, can be calculated by plugging in the known values. Although performing the calculations by hand is possible, using software tools such as CAD programs or mathematical modeling software streamlines the process, ensuring greater accuracy and efficiency. Sine and cosine functions are central to this process, as they provide the means to calculate how far and in which direction the third point is from the base. These functions are adaptable, allowing for flexibility in different coordinate systems and orientations. They are also essential in more complex models, where curves and arcs are involved. In these cases, the curves can be approximated by breaking them into smaller, simpler triangles, each of which can be calculated using the same principles of trigonometry. Overall, the use of trigonometric functions like sine and cosine, along with precise initial measurements and mathematical software, enables the creation of complex shapes and models in CAD. By systematically defining the components of triangles and ensuring the accuracy of each step, designers can construct intricate systems of interconnected shapes, optimizing both the modeling and calculation processes. This approach ensures that the final model is both accurate and efficient, minimizing the potential for errors and reducing the complexity of the design task. In the process of parametric modeling and object representation, coordinate systems like rectangular, XYZ, cylindrical, and spherical are used to describe shapes and their properties. These systems are especially useful when working with parametric equations for curves and surfaces. Cylindrical coordinates are ideal for objects resembling tubes or cylinders, while spherical coordinates are well suited for modeling spherical or curved surfaces. When you're creating an object parametrically, you're essentially defining a coordinate system that gives rise to the use of parametric equations. These equations can be rectangular, cylindrical, or spherical, and they allow for mathematical modeling of the object's shape. By manipulating the parameters of these equations, you can generate both simple and complex geometries. For example, a parametric equation for a helix might include parameters for the angle of rotation and height, enabling the creation of intricate forms. The use of parametric modeling hinges on defining the object's geometry through equations that express the coordinates of points on the object as functions of one or more parameters. This approach is highly flexible and allows for precise control over the shape of objects, enabling the inclusion of features like curves, twists, or scaling. Parametric equations are particularly effective for modeling complex surfaces, such as Bezier curves or NURBS, non-uniform rational B-splines, which are commonly used in computer-aided design, CAD, and other computational fields. One of the key benefits of parametric modeling is that it provides an efficient way to manipulate geometry. Changes to the parameters directly alter the shape of the object without the need to rebuild the model from scratch. This makes it easier to update designs and incorporate changes, which is a fundamental principle of modern computational geometry, animation, and physical simulations. While parametric modeling can be done manually through mathematical equations, CAD software automates much of the heavy lifting. Tools like splines, rectangles, and circles in CAD software are predefined geometric entities. When you draw these shapes in the CAD workspace, the software automatically generates the underlying parametric equations, saving time and allowing the user to focus on design rather than mathematical calculations. However, for more complex tasks, CAD designers often have to program or use libraries in their software ecosystem to handle advanced parametric modeling. CAD software also allows for the definition of dimensions and constraints that govern the geometry. For example, you can define the width and height of a rectangle as parameters, and adjusting these parameters will automatically update the geometry. This level of control is vital for producing accurate, detailed designs. Behind the scenes, CAD software uses mathematical formulas to manage the geometry. For instance, a circle drawn in CAD is mathematically represented as x equals r asterisk cosine, t, and y equals r asterisk sine, t, where r is the radius and t is the parameter that determines the angle. Similarly, a spline might rely on polynomial equations to calculate intermediate points between control points. When transitioning to 3D CAD, the software expands the coordinate system to include the z-axis, allowing for the creation of three-dimensional shapes using tools like lofts, sweeps, and extrusions. In 3D modeling, extrusions are used to create 3D shapes by extending a 2D sketch along a straight line. For example, extruding a circle creates a cylinder, and extruding a rectangle forms a box or a prism. This process is useful for generating basic shapes such as columns, beams, or pipes. Sweeps and lofts are more advanced techniques for creating complex geometries. A sweep creates a 3D shape by moving a 2D profile along a specified path, while a loft creates a shape by smoothly transitioning between multiple 2D profiles at different heights or positions. Lofts are particularly useful for creating organic, flowing shapes. For example, lofting a circle to a square creates a tapered or flared shape, while lofting multiple irregular profiles together can produce more complex organic forms. These techniques are essential in fields like industrial design, architecture, and animation, where smooth transitions and intricate geometries are often required. When mapping complex objects, such as the human body, without relying on physical measurements, parametric modeling can be extremely helpful. One approach is to take multiple shots from different viewpoints to capture the surface or body of the object. This data can then be used to create a 2D parametric outline of the object, often using rectangular coordinates, x, y. From there, you can use techniques like Delaunay triangulation to form triangles that will serve as the mesh for the 3D model. These triangles provide structure and allow for interpolation, a process that helps smooth the surface between known points. Interpolation, in this context, refers to the process of inserting new data points between known points to create a smooth transition. It's a key component of parametric modeling, as it allows for the introduction of more complex features into the geometry. Extrapolation, the process of extending beyond the known data range, can also be used to manipulate geometry further, especially in cases where you want to generate shapes or features beyond the original parameters. As parametric equations are inherently flexible, they can be expanded to introduce more complexity. For example, you might start with a simple parametric representation of a rectangle, and then modify the equations to add curvature, transforming it into a rounded rectangle. By introducing additional parameters, you can control specific properties like scaling, rotation, and deformation. This makes parametric equations powerful tools in geometry and modeling, as they can describe everything from simple objects to intricate, curved surfaces. In practical applications, parametric systems are modular and adaptable. They allow for the creation and manipulation of complex shapes, which is why they are widely used in fields like computer graphics, CAD modeling, and animation. For instance, when modeling complex surfaces or bodies, triangular mesh modeling is often used. This technique involves dividing the surface into interconnected triangles, which help approximate the complex shape. However, due to the inherent nature of triangles, there will always be gaps between them. These gaps can be bridged using mathematical functions like sine, cosine, and tangent, which help to smooth out the irregularities and complete the 3D surface. Ultimately, the combination of parametric equations, interpolation, and triangulation provides a powerful framework for creating and refining complex models. Whether you're working with simple shapes or intricate, organic forms, parametric modeling offers the flexibility and precision needed to bring creative designs to life. In a purely mathematical sense, a triangular mesh does not leave gaps between triangles because the vertices are shared, and the triangles are interconnected. However, when approximating a surface, the mesh introduces geometric irregularities due to the inherently flat nature of the triangles. These irregularities mean the mesh cannot perfectly replicate the smooth curvature of the original surface. To address these discrepancies, mathematical functions such as sine and cosine become crucial. These functions define smooth transitions across vertices and edges, improving the mesh's ability to approximate curves. Interpolation and smoothing techniques often leverage these functions to blend the geometry, resulting in a more accurate representation of the underlying curved surface. For example, the normal vectors of a surface might be interpolated using these trigonometric functions to create the perception of smoothness. Tessellation shaders can dynamically refine mesh details by utilizing sine and cosine functions, effectively filling in visual gaps. This refinement process enhances both the visual and computational geometry of the mesh. Advanced mathematical methods like parametric surfaces, NURBS, non-uniform rational B-splines, or subdivision surfaces take this a step further. They improve upon the triangular mesh by mathematically defining smoother surfaces that the mesh approximates. For simpler cases, sine and cosine functions are employed in texture mapping or displacement mapping to simulate smoothness on a rough mesh. While a triangular mesh itself doesn't have physical gaps, its flat nature introduces approximation errors. These errors must be mitigated through mathematical smoothing. Trigonometric functions are pivotal in these corrections, enabling smoother transitions across the mesh. In the context of parametric 2D representation meshes, spherical trigonometry becomes essential for handling geometric properties like curvature. Sine and cosine functions help define the positions of points along circles or curves. For accurate depth and curvature data, concepts like great circles, the largest circles on a sphere, are often used. These great circles are particularly effective for representing curves that follow the surface of a sphere or other rounded objects. Using spherical trigonometry, you can build 3D models of objects. The points derived from triangulation provide the structural framework, while sine and cosine functions ensure proper representation of curves. The final mesh enables the calculation of precise depth and curvature using known scale factors and geometric principles. By integrating spherical trigonometry with sine and cosine functions, along with parametric modeling techniques, highly accurate 3D models can be created. These models allow for physical measurements of every part, providing a comprehensive understanding of the object's geometry. The key lies in translating 2D data, such as images and scale measurements, into 3D geometry. This geometry is then refined using triangulation and trigonometry to accurately capture curves and depths. By combining these mathematical tools and techniques, it becomes possible to create detailed and precise representations of complex surfaces. Lens distortion is a common phenomenon in imaging systems, where straight lines in the real world appear curved or warped in a captured image. This distortion is typically modeled mathematically using predefined equations, such as the radial distortion model. However, when working in dynamic environments, these predefined models may not accurately represent the unique characteristics of the lens and scene. This essay explores an adaptive approach to lens distortion mapping, emphasizing real-time focal point identification, dynamic equation generation, and logical understanding of distortion. This method transcends reliance on predefined coefficients and aligns more closely with the spatial and logical realities of the imaging process. The radial distortion model is a widely used framework in optics, defined by the following equations. X distorted equals X times 1 plus k1 are 2 plus k2 are 4 plus k3 are 6. Y distorted equals y times 1 plus k1 are 2 plus k2 are 4 plus k3 are 6. Where x and y are the original coordinates, r equals square root x2 plus y2, is the radial distance from the center of the image, focal point, and k1, k2, k3 are distortion coefficients specific to the lens. While effective in many cases, this model assumes the distortion behavior is well characterized beforehand, making it less suitable for dynamic scenarios where distortions must be understood in real time. Rather than starting with predefined coefficients, the dynamic approach begins with observation and measurement. This method involves placing a controlled reference, a backdrop with a checkerboard or dot matrix pattern, into the scene. The dimensions of this pattern, h, for height and w, for width, provide a known baseline for comparing the distorted image captured through the lens. The first step in this method is to map the lens's actual focal point by observing how the dots or grid lines deviate from their ideal positions. This step establishes a dynamic center of distortion that reflects the specific characteristics of the lens in its current setup. Unlike static models, this approach does not assume a pre-existing focal point or distortion pattern. The radial component, r, calculated as the distance of a point from the dynamic focal point, becomes a critical variable. Distortions are quantified by comparing the radial positions of the distorted points to their known true positions on the reference grid. This empirical measurement provides the foundation for deriving distortion equations tailored to the specific scenario. Using the observed distortions, a unique mathematical model is constructed to correct the image. This model may take a similar form to the radial distortion equation, with dynamically calculated coefficients a1, a2, a3, replacing the static k1, k2, k3. Warp, r, equals 1 plus a1 are 2 plus a2 are 4 plus a3 are 6. The corrected coordinates are then calculated as x corrected equals x distorted, warp, r. Y corrected equals y distorted, warp, r. Real-time adaptability. This approach adapts to the lens and scene in real time, ensuring accuracy in environments where distortion behavior cannot be predicted. Focus on empirical data. By relying on observed distortions, the method avoids the pitfalls of assuming incorrect or incomplete distortion coefficients. Flexibility across scenarios. The dynamic nature of the model allows it to accommodate unique setups, such as non-standard lenses or environmental conditions. For practitioners with a strong spatial intuition but less confidence in mathematical syntax, this approach offers an opportunity to bridge the gap. The process begins with observable, physical distortions and progresses to logical derivations of equations. This grounding in empirical data facilitates a deeper understanding of the underlying principles, transforming abstract equations into meaningful representations of spatial phenomena. This dynamic approach can be likened to stretching a rubber sheet with a dot matrix drawn on it. The distortions caused by the stretch are analogous to lens distortions. By comparing the warped positions of the dots to their original grid, one can reverse the stretch and reconstruct the sheet's original shape. This metaphor highlights the process of working backward from observation to correction, making the concept more accessible and intuitive. Dynamic lens distortion mapping represents a significant departure from traditional models, emphasizing observation and adaptability over reliance on static coefficients. By mapping distortions empirically, measuring radial deviation, and generating custom equations, this approach aligns mathematical modeling with real-world complexity. For those who seek not only to understand distortion spatially but also to grasp it logically and metaphorically, this method offers a powerful framework for bridging intuition and precision. Mathematics often reveals itself in the form of equations that describe spatial relationships, and at the heart of many of these equations lies a rooted understanding of geometry. From the concept of square roots to distortion models, to analogies like the diver's rope, these mathematical constructs help us navigate and understand the world of space, distance, and transformation. This essay aims to explore how equations are rooted spatially, using square roots as a foundation, delving into distortion models, and showing how these concepts provide us with a compass for navigating complex systems. Ultimately, It shows how all these relationships stem from the unit circle, a geometric figure that serves as the starting point for many mathematical explorations. The square root operation is central to understanding spatial relationships, especially in geometric contexts. Consider the equation r equals square root x2 plus y2. This equation gives the radial distance, r, from the origin, 0, 0, to a point, x, y, in a 2D plane. The square root here is essential for converting the squared components of the distance back into a linear value. Without the square root, the result would be a distorted measure of distance, e.g., r2, which wouldn't correspond to the real-world distance between the point and the origin. Mathematically, the square root operation serves to root the equation in the true, linear distance. It is as if the equation is grounded in the inherent geometry of the circle. A point in a 2D plane isn't just located by its horizontal, x, and vertical, y, coordinates. The relationship between these coordinates is intrinsically radial, rooted in the geometry of a circle. The square root ensures that this radial nature is preserved in the resulting distance. All of these concepts trace their origins back to the unit circle, a fundamental geometric figure in mathematics. The unit circle, defined as a circle with radius 1 centered at the origin, provides a foundation for many equations that deal with distance and angle in two-dimensional space. The equation for a point on the unit circle is x2 plus y2 equals 1. This equation highlights how any point on the circle maintains a constant radius of 1, connecting the concepts of distance and geometry. The square root operation allows us to extend this idea beyond the unit circle, enabling us to calculate distances for points both inside and outside the circle. As such, square roots are directly tied to the geometry of the circle, helping us navigate distances in spatial terms. To further understand how equations are rooted spatially, we can turn to the metaphor of the diver's rope. Imagine that we are underwater, and we have a diver at the end of a rope, diving deeper into the ocean. The rope's length represents the distance from the diver to the surface. If we imagine that the diver's rope is attached to the center of a distorted system, such as a lens or a non-ideal optical space, then the length of the rope changes dynamically based on the level of distortion in the system. In distortion models, like the lens distortion model, x distorted equals x times 1 plus k1 are 2 plus k2 are 4 plus k3 are 6. Y distorted equals y times 1 plus k1 are 2 plus k2 are 4 plus k3 are 6. The terms k1, k2, k3 represent distortion coefficients that modify the distance, represented by r, in proportion to how far the point is from the center. The radial distance, r, acts like the diver's rope, with each coefficient adjusting how much the rope stretches or contracts depending on the distance from the center. As you add more terms, i.e., k2 are 4, k3 6, the rope grows longer, representing the increasing complexity of the distortion. This scaling mechanism shows how equations adjust in a proportional way to accommodate the increasing distance, akin to the diver adjusting the length of their rope to account for the deeper depths or stronger forces at play. Equations like the one above do not only describe positions in space but also encode the orientation and proportionality of those positions. The key to understanding this orientation is the role of the square root and the radial component, r. The square root operation ensures that, no matter how complex the system becomes, the linear relationship between the origin and any point remains intact. In our diver's rope analogy, the square root keeps the diver's position grounded in the spatial system, ensuring that the length of the rope correctly represents the distance from the center. The distortion terms add layers of complexity to this system. Just as the diver's rope might stretch and contract as the depth changes, the terms in the distortion model represent how the space is warped based on distance. However, the square root retains the fundamental orientation of the space, serving as a compass that keeps the equation true to its geometric origins. The core idea that emerges from this exploration is that equations are rooted spatially, serving as maps of the real world. The square root, as an operation, ensures that these maps stay true to the distances and proportions inherent in geometry. Whether we are dealing with the unit circle, calculating distances in a 2D plane, or working with more complex systems like lens distortion, the underlying principles of radial symmetry and distance always come back to the circle and the square root that governs it. Furthermore, as we add complexity, through distortion terms or higher-order equations, these maps remain anchored in their spatial origins. Each new term stretches the diver's rope a little further, adding complexity and precision, but always rooted in the geometry of space. In conclusion, square roots and radial distances are not just mathematical tools, they are the compass that guides us through the complex terrain of geometry and transformation. They help us retain our orientation and proportionality in a dynamic world of ever-increasing complexity. Whether we are dealing with the simple, elegant equation of the unit circle or the intricate distortions of lens models, these spatially rooted equations provide us with a stable reference point that ensures our understanding of space remains grounded, accurate, and meaningful. Ultimately, everything stems from the unit circle, and through square roots and the geometric principles they encapsulate, we are able to navigate, understand, and manipulate the world of space and its distortions.